Welcome to a new year, 2017, and another live session for the online courses. Floor is open for any question on astronomy.
So the first question is from one of our live viewers, and they ask, in the course, you talk about theories that predict more than 3 spatial dimensions. Is there any theory predicting more than 1 temporal dimension?
That's a good question, interesting question. No conventional theory predicting more than 1 temporal dimension. There are sort of variants of standard cosmology which invoke imaginary time, where time mathematically has a real and an imaginary component. Where, you know, and the analogy here is, of course, with quantum theory and the fundamental nature of matter, where it's essentially antimatter in the mathematical formalism of quantum theory is the imaginary component in a Schrodinger equation, where the real component is normal matter. So it's using sort of that kind of mathematics that can lead some theories to invoke an imaginary time dimension. And in the formalism, imaginary time, of course, can flow backwards, so compared to the conventional time that we deal with. So yes, there are sort of variants of cosmology that invoke a second time dimension, an imaginary one, possibly one that runs backwards, and where entropy, you know, will decrease rather than increasing. And that's an interesting concept. But there's no indication as yet that these have any physical reality or how we would even access these imaginary time dimensions.
Right, the next question is from email, and they ask, I was wondering if you could speak about the recent prediction of a 2-star collision that was announced at the American Astronomical Society meeting, predicted to happen in about 5 years.
Right. So this was one of the more exciting press releases at the astronomy meeting that just happened. A number of people in my group were there. I was there. It was in Grapevine, Texas. So the American Astronomical Society meets twice a year. There's a winter meeting and a summer meeting. The winter meeting is usually the large meeting. It, for instance, has a job center where many grads and postdocs look for employment. And there's always a set of press releases of newsworthy topics in astronomy. And the colliding merging star prediction was one of the more intriguing press releases. This is a system where the orbital parameters are well determined, and also it's clear that the stars are already in a common envelope. These are massive stars with extended envelopes. And so based on our knowledge of their luminosity and mass, we know, and the orbital period, we know that they're sort of in a final phase where, because they're in a common envelope, the envelope is acting as a drag on the system, and so it's going to lead the 2 stars to spiral into each other to the common center of gravity. And those orbital parameters allow you to put an estimate on the time this will take, and that's what leads to the prediction. Now, those models, as the paper behind the press release always gets into a little more detail, those models are somewhat uncertain. So I would say the prediction of an eventual merger, coalescence, or collision, however you want to phrase it, is essentially robust. The prediction of the timescale is a little flexible. So, you know, I would say there's an error of about 1 year, 1.5 years on the prediction. But it'll definitely be an exciting event, and we'll get to watch it play out in real time. It's one of the rare times we get to see stellar scale astrophysics playing out as we watch.
Right, the next question is from Desmond, who's on with us live, and the question is, if there are hundreds of millions of stars in our galaxy, then why is our night sky not as brightly lit as day?
So more than hundreds of millions, there are hundreds of billions of stars in our galaxy. If you count all the way down to the red dwarfs, most of which are extremely faint and not visible, you know, even with a big telescope, they're hard to see. You actually end up at about 400 billion. That's the total census of stars in the Milky Way down to the dwarf fusion limit. Either way, it's a vast number of stars, and so the question of why the sky is not bright is a good one. So part of the reason is that space is big, and so the average distance of these stars is substantial. And light goes down as the square of the distance, the inverse square law. And also in the galaxy, especially in the plane of the galaxy, which is where most of the stars are, in the disk of the galaxy, there's a lot of dust, obscuring material, and that essentially extinguishes or quenches the light. So part of the reason the sky is not bright is that the galaxy is not just made of stars and empty space, it's also made of gas and dust. And that gas and dust provides obscuring material that dims the light of more distant stars. So especially looking in the Milky Way, we can't see nearly all the stars that are present in the Milky Way. The other thing that's happening is if you're not looking in the Milky Way, but looking away from the Milky Way at 90 degrees from the Milky Way, so straight up out of the disk of our galaxy, then the actual number of stars that you're looking through as you look out towards deep intergalactic space is quite modest, because the disk of our galaxy is only about 1,000 light years thick. And so the average distance between stars is a few light years. So therefore, you can do the math that on average, you're only going to be looking past a few hundred stars before you're clear out of the galaxy. And so those few hundred stars are not sufficient pasted across the sky to make the sky uniformly bright. The question, of course, alludes to a more fundamental issue in cosmology, which is why is the night sky not bright if we live in an infinite universe? So the galaxy is not infinite, and that's part of the answer to why the Milky Way doesn't make the sky bright. But what if the universe were infinite and it's filled with hundreds of billions of galaxies, as we think it is? Then Olber's paradox from the mid-19th century asks, why is not the sky bright due to the fact that in an infinite universe, eventually any sight line will hit light, whether it's light from a star in our galaxy, maybe less likely, or light from a distant galaxy, very likely. In an infinite universe, essentially every sight line has to hit a galaxy at some point. And since the number of galaxies goes up as the square of the distance, and the light from each one goes down as the square of the distance, this light should just keep piling up, and eventually the sky should be bright. That's Olber's paradox. So my second part of the answer to the question relates to this larger issue of why the sky isn't bright. And the answer to Olber's paradox is multi-part answer, that the light from galaxies has not had time to fill intergalactic space in the history of the universe, less than 14 billion years. And the second part of the answer is that the universe is expanding, and so those more distant galaxies have had their light redshifted, which means reduced in energy. So there isn't an equal amount of energy or light or radiation coming from more distant galaxies compared to nearby galaxies. It starts diminishing as you go out into space, and that also means the sky will not be bright.
Right, the next question is from one of our live viewers who asks, I was just wondering if you could give a quick rundown of Planet 9, what we know, what we assume, what you personally guess.
So there's a pretty active hunt on for Planet 9. Planet 9, of course, is just a catch-all phrase for a Pluto or larger, something larger, we hope, than a dwarf planet in the outer solar system. And there are various teams involved in this. The Caltech team is probably the best equipped to do the survey themselves, but there are large chunks of skies that have to be surveyed, because an outermost planet, Planet 9, is possibly not going to be in the ecliptic, which is the plane of the solar system. So in a very narrow strip of the sky, it might be displaced by 10 or 15 degrees from the ecliptic, and that's a big swath of sky to search for a very faint distant object, obviously tens of billions of miles away. So the hunt for Planet 9 is ongoing. Most of the groups involved estimate that they will not have fully explored to the faintness required for a couple of more years, maybe 2 or 3 more years. And some of them are optimistic that they'll find a substantially large object there, something worthy of calling Planet 9. And of course, to be called a planet, we now know that the planet has to satisfy the International Astronomical Union definition of a planet, which means it has to be large enough to have formed a spherical shape. Smaller objects like asteroids and comets are typically not spherical. It has to have enough gravitational influence to have cleared out a zone in the solar system of its own, and that's where Pluto falls foul of being a regular-sized planet. And I'd say it's a coin toss, the odds whether such a planet actually exists and can be found. But the people who could find it are doing the work. They have data sufficiently deep to find it. They're obviously looking for very subtle and slight motions, because the apparent motion of such a distant object from day to day or week to week is pretty subtle on the sky. It's very slow angular rate of motion. But the survey data is there, and it's growing, and so we'll know the answer within a couple of years. And my guess is there will not actually be a hefty Planet 9 ever found, but I'm pretty sure, and most people are, that we'll find a handful more dwarf planets.
All right, the next question from one of our live viewers is it possible to create a wormhole even if it's at the atomic level?
So wormholes are hypothetically, they're hypothetical constructs out of general relativity. They're obviously tunnels in space-time that connect two different regions of space and potentially of time in a discontinuous way. Space around us and the space of the universe we know and can explore seems to be rather smooth. There are a number of black holes that we know of, but we've never found interconnected regions of space-time, because space-time seems to be pretty flat and linear where we can explore that. So wormholes remain a theoretical construct, and so they're allowed by general relativity. It's possible that space-time could be curved enough to have a sort of interconnected tunnel, if you like, which would be a wormhole. So they remain hypothetical in that sense. And the size of such entities, if they exist, are most plausibly the size of collapsed stars, because black holes are regions where space-time is pinched off and highly curved. So if you're going to hypothesize a wormhole, then it's most likely to be a sort of something the size of the event horizon of a black hole. The potential for microscopic or subatomic sized wormholes or black holes is possible. It's physically possible. You can have a black hole of essentially any mass if you compress that mass suitably so that it goes within its event horizon, goes down to a Schwarzschild radius. But for a subatomic particle to become a black hole, or potentially create a wormhole interconnecting space on a very small scale, requires, first of all, a degree of compression that's not physically possible by any means. No accelerator, no physical mechanism we have could do that. And of course, it creates something that is on such an incredibly small scale that it almost reaches the quantum limit of space-time itself. So that makes such a construct, even though it's hypothetically possible, really implausible. So wormhole on the scale of collapsed star black holes, possibly, not ruled out. Wormholes on the scale of subatomic particles, exceptionally unlikely, and there's really no mechanism for how they would be created.
All right, the next question is, there are speculations about solar storms these past weeks. How could it affect Earth and the moon? So
solar activity is essentially unpredictable outside of the solar cycle itself, which is a sort of 22-year cycle of sunspot activity, where sunspots are essentially the telltale symptoms of what's going on deep within the sun, with the winding up of the magnetic field, eventually the destruction of the magnetic field, reversal of the magnetic poles of the sun, and then the magnetic field builds. And so sunspots follow that cycle. Solar storms are correlated with the sunspot cycle itself, but they also have shorter timescale variations because the sun is very active in its outer layers, especially the chromosphere and the corona. And those storms on the smaller scale, not the global cycle of activity of the sun every 22 years, those are very hard to predict. They're essentially unpredictable. And so we are often subject to those. Now, luckily, because of the nature of the particles and how they radiate from the sun and are sort of buffered in the solar wind and then by the magnetosphere of the Earth, we have a little time delay. I mean, it takes a little while for those storms to impact the Earth-Moon system. Otherwise, it would be 8 minutes, the light travel time from the sun, and that's not really much warning at all. If you're staring at the sun and then predict some huge hit to the power grid in 8 minutes, there's hardly time to do anything. So we tend to have, of a fraction of a day or even a couple of days notice of a storm that might impact the Earth. The moon is, of course, not protected. There's a magnetosphere of the Earth, which, depending on the orbital situations of the Earth and the moon could sort of be in the lee, in the shadow, if you like, of the Earth's magnetosphere, protected from the solar wind by the Earth. and that protects the moon. But generally, the moon is fully exposed to the solar wind and to solar radiation and solar storms. And so those blast into the moon and hit its surface directly. The Earth is protected in two ways. It's protected by the Earth's atmosphere, which obviously shields us from ultraviolet radiation through the ozone, and from high energy particles just through the air itself. But the Earth is also, and maybe even more importantly, protected by the magnetosphere. So this is the extension of the Earth's magnetic field into space, which acts to deflect any charged particles that hit the Earth. And of course, the solar wind is often composed of charged particles because it's a highly accelerated wind that can include protons. Those are the most energetic particles, positively charged. And so those particles are funneled away, following field lines maybe down to the magnetic pole, but away from the equatorial regions by the magnetosphere of the Earth. And so that's our protection. So we do get warning. They still have an effect. We're not completely buffered or insulated from the effect of these high energy particles. It's also very hard to predict the strength of, we can say what the protective power of the magnetosphere is and our atmosphere, but it's very hard to predict what the energetic input of a particular solar flare or super flare in the worst case is into the medium between the Earth and the Sun, and therefore what is heading our way. That's essentially been very hard to predict historically. So it's a kind of unfortunate situation to be in, because the biggest flares in a particular century can definitely be of a scale where they could take out large parts of a country's national grid, for example.
Right. The next question is from email, and they ask, since a lot of discoveries are made using and combining information from several telescopes, both terrestrial and in space, what are the key holes in resources that are likely to be filled coming up, and which ones will contribute the most when completed? So
in terms of telescopes that combine information from multiple telescopes, these are interferometers. It's an interesting question, because interferometry has historically been the domain of radio astronomers, and radio astronomers have built a succession of more and more powerful interferometers using ground-based dishes and occasionally dishes in Earth orbit to extend the baseline. So I'd say radio astronomy and radio interferometry is in a very healthy situation. These interferometers are being upgraded. Their baselines span the world, which is about as good as you can do, unless we put one on the moon. That would be useful. Where the niche is and where the activity is at shorter wavelengths. Interferometry is easy at radio wavelengths because you just have to phase align these arrays, which means match up the incoming waves and troughs at the different telescopes to within a fraction of the wavelength of radiation. And when it's radio waves, those wavelengths are centimeters or even meters. And that's pretty easy to do with waveguide technology. If you want to do interferometry, combine information from multiple telescopes at optical or infrared wavelengths, shorter wavelengths, you have to line up the waves to within a very tiny fraction of an inch, 100,000th or millionth of a centimeter to the size of those infrared or optical waves. And that has traditionally been hard to do. You can do it with optical fibers. You can do it in a vacuum, through a vacuum, of course. But through air, it's essentially impossible. Variations in the air density and temperature just make it impossible. So I think the opportunity in the niche in astronomy in the next decade is for better optical interferometers, and in fact for near-infrared interferometers. There's a national study that just happened within the last year, looking at the super ambitious projects astronomy might consider for the next 20 or 30 years. So these are huge projects of the order of Hubble Space Telescope, so $5 to $10 billion price tag, the most expensive projects astronomy can ever consider. And one of the highest priority of these potential projects is what people would in shorthand call an infrared VLA. The VLA is the very large array. That's the classic radio interferometer that was built in the late 70s and has been working and doing radio astronomy for decades. The challenge to build an infrared version of the very large array to work at those much shorter infrared wavelengths, that's an enormous technical challenge. It would be a very expensive project, very interesting project, because it would deliver exceptionally high resolution, super sharp images in the infrared waveband, which is interesting because, as for instance, planets put out a lot of radiation at infrared wavelengths, so that would allow us to image planets in other star systems extremely well. So it's very exciting for that reason, and there are actually other kinds of science you could do with an infrared interferometer. So that's the big project that people have their eyes on. But at that $5 to $10 billion price tag, there are other ideas too. And so it's not clear that that one would be given high enough priority to get that kind of money.
The next question is, when is the James Webb Space Telescope due to launch? What's the status?
Due to launch in October 2018. And at this point, after multiple delays and a lot of cost overruns, which have taken the budget well over $8 billion, I think it's close to $9 billion now, that is essentially firm. So James Webb Space Telescope is currently on track. There have been some bumps, well, many bumps along the road, but even recently there were bumps along the road in terms of the readiness of a couple of the instruments. But the telescope assembly, the quality of the mirrors, the integration of the telescope assembly has been conducted. All the instruments on the telescope have been through what they call the thermal vac test, the thermal vacuum tests, which takes place at Goddard Space Flight Center or Johnson Space Center, where the instruments are put into as close to pure vacuum as you can do on Earth, and subjected to an intense radiation environment as they would have in space, and subjected to a lot of shaking and jostling as they'll experience during launch. And so they're given like the biggest workout you could imagine for an instrument that will eventually be in space. And so the instruments have been through that, and they're currently being integrated into the optical telescope assembly. So the whole James Webb Space Telescope is being put together. And that's as it should be, because with less than 2 years to launch, the preparation for launch takes a long time. So integrating the telescope assembly with the instruments and doing the final test of everything all put together is going to take a good part of a year. But basically, the launch window is intact. There's unlikely to be any delay unless it's like a weather delay right near the launch date. And James Webb will go off. And as everyone knows, it's going to an unserviceable location 1 million miles from the Earth. No shuttle astronauts, no rescue for this telescope if it malfunctions or fails. And it has to deploy while it's at its location. The telescope will be in a folded configuration in the launch vehicle and will unfold to its 6.5-meter diameter once it's on location at the Lagrange point, 1 million miles from the Earth. So that's the high stakes part. I think that part gets engineers at NASA, more nervous than the launch itself, the deployment of the telescope. And so we'll see that at the end of 2018. By the end of 2018, we'll know if the instruments work, if the telescope's unfolded and fully deployed, if the solar panels deploy. They also have to fold out to the size of a football field to deliver enough power to run all those instruments, and all of that will be known, and the first images will have been taken by Christmas time, I think, on 2018. A nice Christmas present for astronomers around the world if it all plays out.
Right, the next question is from a live viewer who asks, can you share with us your opinion about the similarities between an atom and a solar system?
So the Atomic Energy Authority, going back to the 1950s when it was formed, they developed this sort of little emblem which made the atom look like a little solar system. It had a nucleus, and the electrons were just shown in little orbits at different orientations around the nucleus. And it's a very iconic symbol. It's part of our culture, essentially, to think of the atom as a miniature solar system, with not like our solar system where all the orbits are in a plane, but where the orbits are randomly oriented. And even at the time, physicists, pointed out to whoever designed that for the Atomic Energy Authority, that's not really right. So, you might want to use a slightly different symbol. But of course, I don't think it's a bad symbol. It's iconic. People recognize it. People understand it. You find it throughout the popular culture on the web, used in all sorts of different ways. But the reason it's inappropriate is, of course, it doesn't align at all with the way quantum theory says the structure of the atom actually works. So electrons are not in orbits around a nucleus. The electrons first are not localized. They're quantum entities, and so they're fuzzy, they're diffuse, if you like. They don't have sharp edges at all. They're more like wave functions or waves than they are like particles. And also they have discrete energies. So they are not, whereas a solar system, a planet could have any energy, you could have an orbit at any distance from a star. The quantum energy levels are discrete and unique, and so that's not like a solar system either. So in terms of energy, in terms of localization of the object, if you want to call it a particle like an electron, it's a sort of inappropriate analogy. And that's fine. It's as long as scientists and even the general public recognize that it's a metaphor or an analogy and not literal, then I still like that symbol.
All right, the next question is, what are your thoughts on the Nemesis theory of two suns?
So this is sort of in the same category as the planet X, or ninth planet. It's the idea that there's a sort of shadow sun, that there's a second object, a dark object that cohabits our solar system. And these ideas didn't really emerge in a normal, strictly scientific sense, where you have a theoretical belief that there should be another star or Nemesis object, if you want to call it that. So they were never very well posited in terms of a theory. And then observationally, they've proved resistant to being positively tested. So there is essentially no evidence of a massive shadow sun or Nemesis object in the solar system. If such an object had substantial mass and therefore gravity, we would easily see its influence on the sun and the inner solar system, and we don't see that. And the distance it would have to be to not register its effect on the solar system is, of course, many times the distance from the sun to the outermost planets, at which point it just becomes like a neighboring star. And yes, there are neighboring stars, so it's no longer a special object. So basically that idea has been very completely debunked.
All right, the next question is, do you think that we will see a supernova explosion in our lifetimes?
I think so, and I presume the question really means, do I think we'll see one in our own galaxy in our lifetimes, which would be a spectacular event, almost certainly a star visible in the daytime sky. And I think so, and I hope so. The Milky Way is essentially overdue because models of stellar evolution, and we know what the galaxy is made of pretty well and how many stars there are. We know how long those stars live, and we know how many are massive enough to die as a supernova. So all of those calculations, the most generous bounds on the supernova rate for our galaxy is 1 every 50 to 100 years. I don't know of any calculation that say it's more infrequent than about once a century. But the last one was 4 centuries ago. So even recognizing that these are random occurrences governed by Poisson statistics, the probability with an average event rate of 1 per century that you wait 400 years for the next one is actually low. I don't remember the number, but it's a few percent or less. And if the rate was really 1 every 50 years, the probability of having to wait 4 centuries is a fraction of a percent, small fraction of a percent. So the answer is we're totally due. Unfortunately, they're not predictable because we can't identify a star in the sky and say exactly when it's going to go off. I mean, we can identify stars that will die as supernovae in the solar neighborhood even, but we can't say how close they are to dying within the level, at the level of a century or a millennium. So we can't predict it, but we can say statistically that it's likely to happen. And that's exciting because that means, as the question asks, that within our lifetimes, for say a few decades, we should really see this happen. Now, the place where we might get unlucky is if the supernova goes off on the far side of the Milky Way in the disk, essentially behind the galactic center, so sort of in the direction of Sagittarius, roughly, in the sky. The Sagittarius, the sight line between us and the center of our galaxy, has so much dust that only 1 in a trillion photons gets to us from the galactic center. Visual photons. If you go to the radio, they all get out, and infrared, most of them get out. So if a supernova went off on the far side of the galaxy through the plane of the galaxy, we might not even see it. I mean, not far from being visible in the daytime sky. It might just be totally not visible at all. That's just bad luck. If it goes off on our side of the galaxy, or in the solar neighborhood, or out of the plane of the galaxy, then it's going to be a hugely bright and impressive event. Visible, again, potentially, if it's less than 100 light years or so, in the daytime sky.
All right, the next question is from a live viewer. What is the importance of the recent discovery by radio astronomers of fast radio bursts as bright as 500 million suns?
So this is a new, it's not a brand new discovery. Fast radio bursts have been known for a number of years, but they sort of hunting down of the phenomenon has happened more in recent times. So fast radio bursts, as implied, they're sort of extremely intense bursts of radio energy that can be concentrated within even a second or a few seconds. Sometimes they repeat, sometimes they don't repeat. And they are found, when you look at the optical objects, many of these bursts are found in quite distant radio galaxies, quite distant galaxies, so billions of light years away. So that's where their incredible brightness, their luminosity comes from. So these are sort of stellar cataclysms, you know, of the same order as a supernova, but much more energetic, sort of like a hypernova or a gamma ray burst. These are the most similar type of phenomena we know of that just happen to be putting out a lot of energy in the radio band. And I would say the physical mechanism of these bursts is still not understood. There's probably 3 or 4 theories that are out there for what could cause these. You know, there was a speculation, of course, and it got into the media, that these rapid bursts might be aliens trying to signal us or something like that. There might be artificial signals, but that really has gone away, because we do understand that stellar cataclysms can make fast, rapid radio bursts, just as pulsars made fast, rapid radio bursts when a star collapses and dies, and that was discovered decades ago.
All right, the next question is from email, and it is, how is the detection of gravitational waves different on Earth and in space, like LIGO versus eLISA?
So LIGO is a stunningly successful experiment, of course, now having detected 2 strong binary black hole mergers and a third one at a weaker level of significance, but you know, the people in the experiment think it's pretty good detection. And we expect more of those to come. But LIGO is only able to detect the ringing of gravity waves, the sort of frequency of gravity waves in a particular range. At the high frequencies, LIGO is limited by essentially noise in the electronics, shot noise in the electronics. So for gravitational wave frequencies of much more than a few hundred hertz, LIGO loses sensitivity. It loses it kind of gradually, so it still has some sensitivity out to about 1,000 hertz, but not much after that. But at the low frequency end, LIGO has a really hard limit on its detection capability, and that's caused by geological noise. So even though LIGO detectors were built at the 2 quietest places you could find geologically in the continental US, which is Hanford, Washington, and in southern Louisiana, Livingston is the nearest town, there's geological activity. Everywhere on Earth has geological activity, and that geological activity typically is just sort of little rumbling seismic motions. They're very small scale, but it doesn't matter because this is such a sensitive experiment, with frequencies of from 1 hertz down to about 1/10 of a hertz. That is one oscillation seismically every 10 seconds. And that's a very strong background or contaminating noise that kicks in at those low frequencies. So LIGO is completely obliterated in its sensitivity at those low frequencies. So therefore, if you want to find lower frequency gravitational waves, you can't do it on the ground. Now, why do you want to find lower frequencies? Because the simplest way to think of the type of event LIGO is looking at, black hole mergers and coalescences, is that the frequency of the gravity waves is related to the mass of the objects. The lower the mass of the object, the sort of more rapid its orbital time scale, and the more rapid the ringing timescale of the gravitational waves when the objects merge. So for stellar mass black holes, the final crescendo is called a chirp signal in gravitational wave parlance. The chirp signal is tens up to a few hundred hertz. And those are black holes, of course, of a few tens of solar masses. If you were interested in looking at what happens to the merger of galaxy center black holes, or the nuclei of galaxies, those are millions of times the mass of the sun. So when two galaxies merge, their black holes are millions of times the mass of the sun, and so millions of times more massive than stellar mass black holes. And so their orbital times are going to be millions of times larger, and their frequencies of gravity waves will be millions of times slower. And so they're firmly in the regime where you couldn't possibly detect them from the ground, because instead of a hertz down to a tenth of a hertz, you're talking about 10 to the minus 6 hertz or 10 to the minus 7 hertz. And if you think about that, that's pretty amazing. That's one oscillation or wave in a million seconds. So years is the time scale of a complete gravity wave oscillation. And the only place with the stability or the baseline between different detectors to do that is space. And that's where the eLISA design comes from. eLISA is designed to be a free-flying interferometer out in deep space with a minimum of 3 elements. So you can sort of form arms in 2 directions or make a triangle and look at the baselines between A, B, and C and any pair of A, B, and C. And eLISA is spread over millions of miles, so the baselines are much longer. And because it's in space, the stability is sufficient to look at waves that take months or years to do a complete oscillation. And so that's what you're trying to do. So eLISA, by being in space, gives you the option or the opportunity to detect gravity waves whose frequency is so incredibly low that you couldn't possibly detect them from the Earth, but that opens you up to looking at black holes that merge in the center of galaxies. It's a very exciting experiment. It's a completely different experiment. It's the same principle, but the astrophysics is so different from star black holes merging. And eLISA got a huge boost, of course, by LIGO's detection. It already had some seed money, but basically now it's been fast-tracked for technology development, and nobody's found a showstopper yet. We know how to make interferometers, and we know how to make them in space and make them work. The actual very clever thing about eLISA is that each of the 3 spacecraft, just imagine 3 spacecraft for a minute, will have a Michelson interferometer in it, and that Michelson interferometer is actually free-floating within the spacecraft. And so the goal of the eLISA design is to have the interferometers essentially not having any net motion with respect to the spacecraft that surrounds them. So the spacecraft has little tiny thrusters in it where the spacecraft moves to keep the interferometer element at the middle of the spacecraft, and that you don't touch the interferometer element, you just let it be sitting there inertially in gravity, in a local low gravity situation. It's very interesting physical and engineering experiment that we really think we can do.
All right, the next question is from a live viewer who asks, does machine learning have any applications in astronomy?
It does, and it's been limited so far. AI or machine learning is used in various niche ways, I would say, in various niches. One of the ways it was used first and very powerfully is in scheduling the Hubble Space Telescope. So Hubble Space Telescope, the astronomy's premier facility, obviously has an enormous requirement to be used efficiently because it's so expensive and everyone wants to get time. Hubble has 120 or maybe closer to 200 different instrument modes, combinations of spectrograph, filters, etc. It also has to look at targets all around the sky. It has to conserve fuel as it moves around the sky, do so as efficiently as possible, have as few instrument changes as possible, and it has to merge in a given cycle or 1 year period the proposals of 100 different astronomers all doing different types of science. It also has to avoid the South Atlantic anomaly. It has parts of its orbit where things are not visible. It has to avoid looking at the Earth and the Sun. So if I made a list, that's a lot of constraints. And rather than try and do that with a simple algorithm or have a very clever programmer do it or do it by hand. The project used AI algorithms, sort of learning algorithms to optimize the efficiency of the scheduling. And so humans do not intervene in that. The schedule is spat out of this very sophisticated and AI type software, and it's been working for over a decade. It does a really good job. The other area, of course, where AI methods can come into play in astronomy is in pattern recognition and detecting signals in the presence of noise. So for pattern recognition, that might be involved in like galaxy classification, because galaxies are faint fuzzy blobs. They have some symmetry, they have some structure, they have noise, and they have their common features, which an astronomer can recognize, of spiral arms and nuclei, are just the most gross features of a galaxy. So AI algorithms have been used to tease out much more subtle patterns in what's going on in galaxy structure and morphology, and they've had some very interesting successes in that. In a more abstract sense, you can also use AI algorithms to filter signals from noise, whether the signal is something like a gravitational wave signal. Algorithms sometimes use that method too for gravity waves, or whether it's trying to find a planetary eclipse signal from noisy data of Kepler. So people have deployed machine learning or AI type algorithms in, I would say, a pretty wide range of astronomical applications with some success.
All right, the next question needs a little clarification, but the question is, what are we going to learn from Huygens on Titan? Well, I want to clarify that Huygens landed years ago. So
right.
You can talk about what it did.
So Huygens was 2005, as I recall, around Christmas time. Huygens was the lander that separated from Cassini. Cassini is the mission that's still working in the Saturn system, exploring moons in the Saturn system, done some amazing work. Well, back when it arrived in the Saturnian system, the Cassini deployed a lander built by the Europeans that was the Huygens probe, and that landed. It delivered, actually, I think it was formally less than an hour of data, but it was the first time humans had ever soft landed on a distant object other than the moon or Mars in the solar system, certainly anything in the outer solar system, and it was Titan. And that mission, the Huygens probe, has been fully reduced. All the data from it has been reduced now some years ago, and we've learned as much as we're going to learn from Huygens. It was very successful. It wasn't completely successful because one of the cameras had a problem, and so they essentially lost half the data. And so they had to sort of interpolate, the camera was spinning, so the probe was spinning as it went towards the surface. And when you watch videos of it, they've essentially done the clever trick of interpolating the missing part of its coverage from the loss of the second camera, and they've sort of despun the otherwise dizzying view the camera actually had to give you a sort of smooth flying down sense of what Huygens did. If you watch the animations, you're seeing a lot of clever processing. The probe also made measurements at the surface. It wasn't just a visual descent. It also had spectrometers. It was sniffing the gas as it went down through the atmosphere, pressure, temperature, chemical composition. And then it was very particularly interested in what happened at the surface, because there's liquid there. There's frozen and liquid versions of ethane, methane, ammonia, and water. And so the probe was very cleverly trying to measure as much as it could of those gases and liquids as it hit the surface. But the battery didn't last very long. It was very far from any source of solar radiation, and it didn't have solar panels or anything. So it only had a fixed battery life, and it only lasted, I think, 40 minutes. I can't remember the exact number. So not much. That's all the data we've ever had from Huygens, and it's all been reduced and put out there now.
All right, the next question is from one of our live viewers that asks, can you comment on recent news that the moon is 4.51 billion years old and may have been formed within 60 million years of our sun forming?
Yeah, so the data on the moon and Earth ages has improved over time. We've obviously had moon rock. We've had 450 kilos of moon rocks sitting mostly at Johnson Space Center since the Apollo landings of the late 60s, early 70s. And those rocks have been used to put a pretty firm age on the moon. And those age estimates keep getting refined because the lunar samples from the different Apollo landing sites, they didn't all contain primordial material. So it takes a fair amount of research to find the most primitive material and project back to the true age of the moon. But people have done that. Now, the age of the Earth is similarly measured and is more complicated because the Earth is a dynamic planet, so it's really hard to find unaltered rock. It's essentially impossible to find completely unaltered rock. So there's always a little bit of inference and a little bit of extrapolation involved in age dating these rocks, and that's independent of the issue of the radioactive decay method that you use. And typically for moon and Earth rocks, two different isotope parent-daughter isotope pairs are used to do a cross-check. So these are pretty reliable numbers, and this number that was mentioned in the question of 4.51 billion years for the moon is to be compared to 4.54 plus or minus some error bar billion years for the Earth, and that difference of 40 to 60 million years is presumably the time after the Earth first formed, where the moon was splashed off by an impact with a Mars-sized object. That's the current model, and a lot of data fits that model. So these new ages have sharpened that timeline because they pin down how soon after the Earth formation that giant impact happened that spun off the moon. And that measured time difference of 40 or 50 million years is consistent with the models. It's consistent with the fact that there were big enough pieces of debris around that time that the moon formation should have been very quickly after the Earth formation. So this story sort of hangs together, and these recent age estimates have just sharpened the story and made us more confident that we know how the moon actually formed.
All right, the next question is from our live viewer who asks, is there a black hole in every galaxy center?
We think so, but that's not proven. We know the best evidence for any black hole, and I include now stellar black holes in the solar neighborhood, is the black hole in the center of our galaxy, which is about 4 million solar masses. That black hole mass estimate and its existence and its nature as a black hole is now given to us by watching stellar orbits over 2.5 decades of dozens of stars responding to the intense gravity of the black hole. So that's a stunning measurement that's grown in confidence in the last decade or so. So we have no doubt that our galaxy has a black hole. And that's a pretty small black hole, because you can go through tens of millions of light years from the Earth to M87, an active galaxy, a big elliptical galaxy, and find a black hole that's 3 billion times the mass of the sun, so almost 1,000 times bigger than the black hole in the Milky Way. And that's a big elliptical galaxy, but it's not 1,000 times more massive than the Milky Way. So there's obviously an intrinsic range in the black hole that can form in any particular galaxy. So over a decade or more, Hubble has done really painstaking work on the centers of galaxies in the nearby universe, by which I mean within a few tens of millions of years, so millions of light years, so out to the Virgo cluster typically, and has indeed shown that in every galaxy it can inspect with its high-resolution spectrographs and super sharp imaging, a black hole can be found. There are small black holes, inactive black holes in our nearest neighbor galaxies, M31 and M33. So far we found no exception to the rule that every galaxy has a black hole. Obviously it's extrapolation to say, and it's induction to say that therefore every galaxy in the universe has a black hole. But so far, based on our measurements, that can be supported. And also we think we know the mechanism by which black holes will naturally form at the center of every galaxy. What's highly variable, however, is how those black holes grow and how they feed and how bright they are. And so a small fraction of those black holes at any given time are active. And when they're active, of course, they're pumping out huge amounts of energy so that the black hole and its immediate environment outshine the galaxy by factors of hundreds, maybe even thousands. And very few black holes are doing that at any given time. So most of these black holes that we find in the center of galaxies are dark and pretty hard to find unless you use this fine imaging the way Hubble has done in the nearby universe.
All right, our last question for today is from a live viewer who asks, by when do you think we are going to be able to travel to another star system?
Well, if the we is us as a species or as biological organisms as opposed to we, our technology, then I say the answer is centuries. Breakthrough Starshot is a project that was announced last year, funded by Yuri Milner, with a sort of star cast of scientists involved. And that's a project to accelerate nanobots powered by solar sails to a few percent of the speed of light and reach Proxima Centauri, the nearest star system, within a couple of generations, maybe 50 years. So we have the technology already, or within a decade, to accelerate tiny little space probes with sensors that could measure things and take pictures to a nearby star system. We could get that project running within about a decade, and it would get to its nearest star in 40 or 50 years. So that's the time scale for nanobots. For spacecraft that carry humans, and those humans would almost certainly have to be in suspended animation and therefore be reanimated when they got to their target, because they're not going to be traveling at more than a few percent of the speed of light, maybe even less. So the journey time, even to the nearest star, is centuries. That is an incredible undertaking, because the energy cost of accelerating a spacecraft big enough to hold a bunch of humans, even say a dozen, is phenomenal. It's more than the energy consumption for a year of the United States, or perhaps even the world, to accelerate a spacecraft to even a percent of the speed of light with that much mass. So we almost need new propulsion methods to do that, which is why I'm going to put that off for a couple of centuries. So appreciate your questions, and actually out of the sync of the questions, I'll mention something that we're going to have on our Teach Astronomy website. So we are approaching 50 of these live sessions over the last few years, and we have developed a method whereby we can parse the questions and have a text box where you can enter a question on our website, and it will search all that video material, and instead of having people wade through the material and watch it beginning to end, hoping that they found a question and an answer they were interested in, you can randomly access the material, all of it, to hopefully answer your questions. So for all of you who are participating in these live sessions, we hope that's a feature you will enjoy.